Next, I would like to discuss Theme6 just in general. Where does it fit in when you do design? The most important thing is actually for people that is interested in data, gathering data. Because if you want to design a reactor, the first thing you need is the kinetics. You need someone to either measure it in a lab. So your company will have a lab facility, a research facility where you will do experiments on a lab scale, normally with little batch reactors, or sometimes with small little plug flow reactors, like some of the problems you will see. It's very small reactors, 4 centimeters, 15 centimeters, for where you will study the back bed behavior of these catalysts and when catalysts are developed. So you will be responsible for measuring the data, and then you will have, of course, you will have concentration profiles with time for your reactants and your products. So B will do that, I will do that, and based on runs at several different temperatures, you will be able to say, okay, this is the shape of my rate equation. This is where it comes from. And that is what you will have to look for and use when you design your reactors in CPJ. Is you will need to source literature of other people's work, so published work where people reported rate expressions. The most important thing first when you start designing your reactor is to make sure that they took cognizance of the effect of external diffusion. So did they think about it? Did they think about the stirrer speed in their CSTR? Or did they just work, or in their batch reactor, did they just work at a single stirrer speed and they generated a few profiles at temperature 1, temperature 2, temperature 3, they fitted the data, they published it, and they said, this is the rate. And now you are going to use that information to design a reactor that's got a completely different shape. So where the Kc value may be the same, maybe different because the shape is completely different. You want to apply it in a plug flow reactor. This was in a batch reactor. The Kc value in a batch reactor is a completely different shape than the Kc value which follows the Teunis-Kramer relationship in a packed bed reactor. So you must make sure that the guy who published the data, or if you are publishing the data, prove to you that the rate data that he publishes is free of external diffusion effects. It's free of external diffusion effects. So this is one of the main things, how you will apply it in your design. Not for this, for semester test and the TATS, I test you on analyzing data where it is in fact constrained, and to realize when the data is constrained by external diffusion effects. So you must make sure that all the experiments are free of that. And how do you do that? Is you investigate some of the information that I publish later on in some of the later videos on the combined effects of all these mass transfer resistances, is if you do 2 runs, one at RPM, low RPMs, so you stir at a lower RPM, let's say 500, and then you do another run at exactly the same temperature, and you've got your catalyst particles and everything is exactly the same, but you stir at 1000 RPMs. And you prove that if I now get my profiles of how my reactant forms with time for run 1 and for run 2, I measure repeat data sets so that I can prove that the stirrer speed didn't have an effect. And if the stirrer speed didn't have an effect, it means I am at that position where Ca bulk is equal to Ca surface. Right, and then you can use that data. You also need to make sure that the researcher proved that Ca surface is equal to Ca bulk, therefore that external diffusion didn't play a role at the highest temperature, where he performed his experiments. Because it's easy to have external, if you look at the temperature profile, it's easy to have at low temperatures to have a regime where you are free of external mass transfer, and where this applies. And then because of the fact that Kc is not really a function of temperature, but the Ki dash, Kcam, Ki dash follows the Arrhenius temperature dependence, means that the delivery of reactant to the surface may not be able to keep up. And then you move into a regime where Ca surface becomes significantly lower than the bulk phase concentration, and even to such an extent that Ca surface may be equal to 0. The implication for that is that those researchers will always measure first order rates. Because if you look at those two rate equations, let's just write it on a mass basis, we get a different pen, Kcam, Ca bulk minus Ca surface, equal to whatever rate expression I have here, and it can be Ca surface to some weird order there. Okay, some weird order there. So if Ca surface pretty much goes to 0, what happens is, okay, if I just consider this rate, it is always going to appear as if this thing, you're not going to see that, and you are actually going to measure in your reactor. You are going to measure the rate of mass transfer. So when you plot this and you say, oh, it is first order in the bulk phase concentration of A, and I measure my K value, what you are measuring is a Kcam and not the true rate constant. And you cannot then see the order of your surface concentration. In some of the videos, I mentioned the example of when you sit in a restaurant and let's say I have a plate in front of me and I am getting some French fries, okay? And I'm waiting for my French fries, and the waitron, over there, ching, 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 brings me a French fry 1 per minute. Okay. So as soon as that French fry hits my board, I am going to gobble it up, okay, because I'm seriously hungry and cross, okay. So I am going to eat that French fry. So the concentration of French fries in my plate is actually pretty much 0. The surface concentration where I can apply my eating rate is going to 0. So there is no way of knowing whether the fact that my plate is full of French fries, this is a plate full of French fries, or just half full of French fries, impacts the speed at which I eat. Okay, because I don't get a chance to see what is the effect of the amount of French fries on my plate on my eating rate. Because as soon as it hits, it's 0. And then I wait. And then another French fry comes and I eat it and I wait. So the rate that is measured is actually this. The rate at which this waiter or waitress can deliver the French fries to my plate. Okay. Whereas if I get a full plate that contains, well, let's say 300 grams of French fries, or a plate that contains 100 grams, will I adjust my eating rate to make this plate last longer because it's less chips on my plate, French fries on my plate, or will the French fries have, what kind of effect will the amount of French fries on my plate have on the rate at which I eat? Okay, so this is a serious consequence, is that often rates are misinterpreted as being first order. And then the order that you are actually, because the diffusion, external diffusion, is always a first order process. So you measure first order, yes, in certain instances when the true reaction rate is actually first order, intrinsic, ching, when it's actually first order, ka-ching. However, you can actually mask this rate when you think you have the surface concentration there, when you don't realize that you are actually measuring this rate, Kcam times Ca bulk. You are actually measuring that rate. Okay, so that is the first reason that you need to take cognizance of that. And because of the temperature effect, you must make really sure that at the highest temperatures, when the rate at which you eat is the fastest, the delivery rate is still fast enough so that this speed at which the waiter delivers the plates of chips doesn't affect the rate at which I can consume the chips. Okay, maybe that's a horrible example. I hope you're not hungry. Okay, so another reason is now when you delve into your design. So now you know. First thing is, so let's just reiterate this. The first requirement is use, or no, let's just be critical. The first requirement is be critical. Be critical of published data. Be critical of that. Read the experimental section of that. Don't just go, I'm not reading any of this, I'm not reading any of this. Ah, there's a right equation. Yippee, this is what I'm going to use for my design. That is how engineers read. Some of the engineers, they read until they find the equation. Where can I plug stuff in and just use that equation as is. Be critical in the way that the right expression was derived at. In terms of, did the researcher, the author of that paper, prove that it was free of external diffusion effects so that I can apply it as is in my reactor? Note, Kc is not translatable from one reactor to another. You cannot. So even if I have a batch reactor, this guy might be using a magnetic stirrer there at the bottom. And that is going to have a different Kc profile to when a reactor is used where I have an overhead stirrer, where it stirs like that. Or if I have a CSTR reactor and I have some baffles there, I'm going, so Kc is a reactor-specific parameter. I cannot say, oh, this guy in his reactor used Kc was that, so therefore I'm going to use a similar Kc. I'm at exactly the same temperature and inlet conditions, and I'm going to use that in my packed bed reactor when I design it. That's not the truth. For the packed bed reactor, you must use the Theme6 correlation, which, thank goodness, is the same for both, at least for packed bed reactors. For CSTRs and for batch reactors, because I have so many different stirrer shapes, I have many different permutations of that Kc equation. Okay, so be critical. That's the first point. The second point is when you now design, make sure that, okay, yes, I apply this rate. I now have a rate equation. Like some of the TUTs, I have published data. I know what my intrinsic rate constant is. I know my rate order. Make sure that the reactor that you design is free of external diffusion effects. Free of it. You don't want to design a reactor where this holds back your rate. So the problem with this is, if you look at a packed bed reactor, Kc, Theme6, is directly proportional to square root of the linear velocity, right? So if I have a thin, very long reactor compared to a fat, short reactor, in terms of mass transfer, Kc in scenario 1 will be much larger than the Kc in scenario 2. Okay. However, which factor, in which of the parameters, which of the design variables that we are now already aware of, I need you to type something, will reactor 1 be bad? Why will my reactor 1 not be the best choice? What will it also affect if I have a long, thin tube compared to a short, fat tube? Can anybody just type something so that I can see that you're still here?
The pressure drop.
The pressure drop? Yes, okay. So heat transfer is definitely affected, but long and thin will be good for heat transfer because my heat transfer area per volume is equal to 4 over the diameter. So the thin one will be better in terms of heat transfer. But in terms of pressure drop, if I think about G squared, so the pressure drop, that K value of mine is directly proportional to G squared. And G squared is G squared is divided, is the mass squared divided by the area. So it's some form of a superficial velocity that flows in that tube. So the smaller the diameter, the higher my K value and the higher my pressure drop. So pressure drop may not necessarily, in these instances, in terms of reactor performance, Kc will always win. It's always better to exclude external diffusion effects and to improve your heat transfer, that one, to improve your heat transfer area. That will always trump reactor performance. What you will need to take cognizance of is when you now have to design your pumping equipment or your compressor to supply the energy to overcome that Ergen equation, is it still worthwhile? If you in order to get rid of mass transfer effects, you must make your reactor tube so thin that it almost looks like little very tiny veins. Does the pressure drop not go so high that the equipment I must buy, for which, if I buy that equipment, for which I'm going to change my screen now so that I can use the eraser. So if I have a compressor for a gas, and a compressor is a seriously expensive piece of equipment. And if I have to operate that and I have to have a very high pressure at the inlet to my reactor in order to overcome my Ergen equation there with the factors, okay? The pressure drop over my reactor. So I need a very high pressure there so that the outlet pressures, as in some of the TUTs, does not fall below a certain minimum value. So that will be a requirement. Not only do I have to pay for that compressor initially, I will also have to pay the electricity bill every month. Add an inert to increase U. If you add an inert, so what happens in your compressor, definitely you can. But adding an inert means that afterwards I am going to have to separate. And once again, that is a seriously expensive unit operation, which comes with its own set of control systems, all you lovers of CPB, that you must implement in internal, keep the reaction rate controlled. Yes, that is what it means, yes. So if I say I want to exclude external diffusion, I want to have high enough linear velocities, high enough RPM rates in order to make sure that I do not have external diffusion effects. Right. Generally, in my experience, in packed bed reactors, where I have a tubular reactor, so not where I have just a big blob, one big reactor and it's adiabatic, it is quite easy to eliminate, it's very rare to find external diffusion effects in those reactors. After Theme7, I will show you some tricks of how to test very quickly whether you need to bother with external diffusion effects. Okay, so for your design application, you will, when you do the designs, you will have to prove to me that you've thought about it in two separate discussions. One, when I evaluated the rate equations that were supplied to me, did I make sure that that guy did his job, because rates that are published that it was subject to external diffusion effects is useless to you. You cannot do anything with it, right? Because you will extrapolate maybe to a higher temperature. So it's not even necessarily true that if you extrapolate that it will be conservative. If you extrapolate to a higher temperature, you may even end up having much lower rates, because it's not extrapolatable, because it's not a true reflection of the temperature dependence of your rate. Okay, so higher you to increase KC. Yes, and we definitely, look, we can also decrease DP, absolutely. So another way of, if I decrease DP, I definitely increase my KC. Great, somebody's watching my videos. So if you decrease DP, once again in the Ergen equation, if you remember the Ergen equation, that K value is inversely proportional to the particle diameter. So pressure drop is never our friend. But pressure drop, that frictional losses, that is as a result of the second law. And we cannot get past that second law. We have to pay. We have to pay the second law. So if I now look at whatever I do to increase KC is going to have a negative effect in terms of my pressure drop. The pressure drop will always increase for all the variables. If I increase my linear velocity, and increase in the pressure drop. If I decrease my particle diameter, decrease in pressure drop. If I add an inert, I'm going to increase the mass flow rate in my tube. So I'm going to increase my G value, increase in pressure drop, right? So just pressure drop can affect the rate, but not to such an extent. The KC will always win that battle. When I just look at the reactor performance, the KC and the heat transfer rates. However, pressure drop needs to be considered when I design. So it's always an overall image that you are after. You want to, when you design stuff, you need to end up with a plant that makes sense in terms of the investment. So are you going to make money in the end? And it's not only the reactor, but all the peripheral equipment that often contributes a big portion of your operating cost, of your capital investment. Your control systems becomes hectic, whatever. Right. Questions on this aspect? More questions? Before we go into that 6.1 and that question about what happens if I have a second order reaction in that 6.1. Nothing. Right, so let me stop